Yes, yeah. Thank you for letting me know. Try to hide this. Yeah. Okay. So, as you said, my topic of the presentation is dissipative energy as a fatigue parameter of additively manufactured aluminum alloy. And on the behalf of all authors of this presentation, I would like to thank you that we can contribute to this conference. Also, I would like to thank Professor Reis, which is on site right now. So first of all, the aims of this work are briefly I will try to introduce you how the specimens were 3D printed, then the measuring setup for measuring not only the fatigue life, service life, and also the thermal parameters that I will introduce you after this. I will show you the experimental results and a method for the fatigue curve prediction based on the self-heating effect, which is based only on 3 samples. So first of all, here are our specimen. On the upper left side, you can see the fatigue specimen, which is left.
Sorry.
Yeah.
The slide is stopped to the first one. If you can
Okay.
skip to presentation mode.
What do you mean by presentation mode? I think that's interesting. Let me see. You can see the slides right now?
No. Yes.
No. Yes? Okay.
Yes.
Okay. I can leave it like this, if you don't mind. Or maybe I can try. Right now you can see the second slide?
No.
No. Okay. Interesting. I've got some. You can press F5. Yeah, I've pressed F5.
You can press F8, F5.
F5. Yeah, I pressed F5. Yeah, I'm sorry for this problem, but I don't know where it is. Okay, I will leave it like this. Now you can see everything, yeah?
Go ahead.
Okay, so these are the aims of this work, and here are the specimens which I was talking about. The fatigue life specimen, which has the radius of transition curve into the diameter of 9 millimeters. And the tensile specimen, which you can see on the lower part on the left side. These specimens were left as printed, but heat treated. The way that they were printed was that at first the contour of the specimen was printed, then after that a small layer up to 2 millimeters in diameter was printed as a skin in each layer, and the core was printed every second layer with different parameters, as you can see in the table. Also, I would like to mention that the roughness values are quite good, even though the surface was left as printed. We made the post-processing procedures, 3 post-processing procedures to be specific. The first series was without the post-processing. The second series was post-processed by recommended values by the manufacturer of this powder. The third and fourth temperature heat treatment were just an interesting part from this for this research, because the 300 degrees should decompose the silicon bonding in the structure and make the structure more ductile compared to the non-heat treated specimen. For the fatigue testing, 11 specimens were used, and for the self-heating testing, step test, 3 of them were used. These specimens were tested on Czech Republic and in Hamburg in Germany, Bavaria to be specific, on the Amsler 100 kilonewton resonant pulsator with a launch control ratio of R equal to 0.1 in compression. Also for the temperature measuring, 2 thermal cameras were used. One was Fluke RFC 600 with 4 millikelvin NNTD, and the second one was American, the FLIR A315 with a little higher resolution. On the left side you can see the tensile specimen, and on the right side you can see the mounting of the specimen in AlSi resonant pulsator and the reference specimen for making sure that we are relying on the difference on temperature and on the exact temperature made by the thermal camera. The results from tensile testing, I would like to point out that they are quite good. Also, the one of the contributing factors with the higher temperature, you can see, I would refer to the yield strength, ultimate tensile strength, and yield strength. That the silicon bonding was decomposed with the 300 degrees heat treatment. As you can see, that the ultimate tensile strength is much lower for the T300 much than the non-heat treated one. Yes. Yeah, and also I would like to point out that this testing series will be redone because the Young modulus is obviously wrong, so no discussion about that. To point out the fatigue curves, as you can see on the left side, I would like to say that all the heat treatment obviously brings up better results in the fatigue curves department. We are using the Kohut-Wiechert regression, which quite well represents the transition from the low cycle fatigue to the high cycle fatigue. Also, the runout condition for the specimen was aimed at 10 million cycles. I would like to point out that the spread of according to the standard deviation was really well for the T300. There were no really significant outliers compared to the T200, but I would like to point out that one of the best performing heat treatment was the recommended by the manufacturer, which was GV Aviation. So let's go to the key point of this presentation, the self-heating effect. The self-heating effect comes naturally during the fatigue testing, dynamic loading. It comes in 3 phases, one of which is the initial phase. This is the first phase, which can be described by the initial incline. The second phase, which can be described with difference of temperature, and the third phase, which is basically the end of the testing, when the crack initiation begins and leads to the fracture of the specimen. You can see that this is the infrared image with the loaded specimen and unloaded specimen. It needs to be visualized because the temperature is nearly null. This is because we are trying to neglect all the environmental effects in the sample surroundings during testing. Also, one of the important stuff here is that we try to make a self-heating step test, which consists of the initial phase and the stabilized phase for about 10,000 cycles in each amplitude. And we are focusing on the stabilized temperature in each step. It was consisting of 15 levels beginning at 30 megapascals under the fatigue limit and reaching nearly around 140 megapascals. So the SN curve estimation was based on the method proposed by Fargione, which says that there is a material parameter that is called limiting energy, which can consist for all the testing specimen. It's invariable on the amplitude of load, and it's the area under the temperature evolution, as you can see here. We'll try to examine it if this is true. I will show you in the second slide here. And also we will try to do that. This is the temperature evolution from the beginning to the failure of the specimen on the single value, but this is the self-heating step test, and we were trying to find out if the limiting energy from the single level test and from the self-heating step test is the same if you do the summation. And by this simple assumption, we could potentially estimate the number of cycles to failure. Because if you look at this graph, we can see that the second phase is generally the longest, because the first phase is somewhere in this testing condition around 100 Hertz with this material, is somewhere around 5,000 to 7,000 cycles. And this phase can be somewhere from, it depends on the amplitude obviously, but it can be from 99% of the temperature evolution to, as higher the amplitude goes, in the second phase gets shorter. So, but with this assumption that you take only the stabilized temperature and do something like a rectangle, you can establish the number of cycles to failure. So we were trying to look at this. We put the average value of the limiting energy from the single level step test, from the single level test, from the normal test on the left side, as you can see, and as the summation from the self-heating test. And we come up to results that are quite interesting, because if you take the limiting energy for the 41, 42nd, and 44 series, the differences in the estimations are not that big. But for the 43rd series, there is a huge deviation, which we were not able to find out why. But here is the estimation, as you can see here. Also, this is the code-weighted regression. We use 3 samples to predict the stabilized temperature and use the limiting energy as a parameter to estimate the number of cycles to failure. Here are both limiting energies, and you can see that there is a good correlation between the line, which is 80% according to the standard of deviation field of 80%. And you can see that there is a good correlation between 10,000 cycles and 100,000 cycles, the slope of the Valor curve between the band, which is typical for aluminium. And the second series, as you can see here, unfortunately I cannot see here because Zoom is not working, but it doesn't matter. But you can see here that there is a good correlation for the T240 series. Also, because the difference between the limiting energy from the self-heating step test and from the single level test is nearly the same. To cut this estimation, we try to use the FKM guidelines, which is a commonly used thing in Germany, that try to cut this estimation by some value. There is a good correlation between for the 240 series, but not so as well for the non-heat treated one. For the 4th series, as I said, it works a little bit worse, but you can see that there is a good correlation using the self-heating step test as a limiting energy. For the T300 series, there is a good correlation of both, although I would like to say that the standard deviation for code-weighted regression was that good that even the red points are outside of the field. Yeah, so this is only the coefficient of determination, and I'm already too long. That I would like to point out that for the limiting energy from the self-heating step test, the correlation of determination is quite good. We come up to quite good results. As I would like to conclude that the tensile test shows probably the best results for the heat treatment of 200 degrees Celsius, but as the silicon bounding is not decomposed, the results are a little bit lower in the fatigue department. So overall results are the best for the T240 heat treatment. Also, I would like to point out that for the T300 degrees Celsius heat treatment, the fatigue spread was exceptional, and we can see it for other series different to this series of testing. Also, I would like to point out that the Fagione method works quite well, but it needs to be there needs to be put a limit for the testing. So in this point, we are trying to introduce the FKM guidelines to it, but in further research, we would like to use the self-heating method directly. Yeah, of course, the further analysis needs to be done for the limiting energy. I would like to thank all the authors of this presentation, and thank you for your attention. And I'm ready to say any questions.